Alright, so now we want to start chapter 13, and this is all about electric circuits. Alright, so what is a circuit? What does it do? How does it produce the light in our light bulbs and run our microwaves and our washers, dryers, refrigerators, etc. Right? So this is all about electric circuits. So the main fundamental concept that we need to start talking about is that of current. All right. So what is current? Well, current is simply the flow of charge. All right, so it's the flow of charge. And while this is not necessarily how it actually works inside a copper wire, say, one way to visualize current is to imagine a pipe. All right, and I have all sorts of particles in that pipe that are free to move. And let's say these are all electrons. So these are all negatively charged particles. It's the electrons that actually flow through the current in a wire. And you can imagine kind of like water in a swimming pool or something, or a river, that the electrons are just going to sit there until I apply some sort of pump, right? So if I have some sort of pump at one end, and some outlet at the other, and I start pumping energy in here, then the electrons are going to flow this way and go through the outlet. And if I have set things up cleverly, then I can set it up so that the cycle then just repeats, and the electrons coming out of this end get recycled and then enter back through this end, and all I have is a bunch of electrons flowing through this pipe. All right, so the flow of charge is what we call current, and this is a decent way to visualize it. This is not actually what happens, but it's a good way to try and visualize what is actually going on. All right. Okay, so what produces the pump, right? What do we use as the pump? Well, the pump would be something like a battery. All right, so the pump is a battery or a voltage source. And if you go and buy batteries from the grocery store or Walmart or Dollar General or whatever, they're going to be rated by voltage. You can buy 1.5 volt batteries, you can buy 6 volt batteries, 9 volt batteries, and generally things that are multiples of 1.5 or 3, right? And so you need a pump, or you need a battery, or simply you need a voltage source. And you need some wire with which for the current to flow. And finally, you need something for the current to affect. And that thing is what we call a resistor. Right? So this is what the current actually gives its power to. All right? So this is where the power is actually used up. All right? So the resistor is where power is used. Or you could say the power is emitted, right? So your light bulbs emit their power, all right? And so resistors come in things like light bulbs, anything that you can hook into an outlet, essentially, so your microwaves, washer, dryer, anything like an appliance. Or in some circuits, especially in small circuits and in computers and things, there are actually literal circuit devices that are called resistors. All right? And so a light bulb or an appliance or a resistor, resistors essentially limit the flow of current. All right, they limit the flow of current. and we'll see how that works here in a minute. And through some tireless investigating, all right, there was a gentleman who developed a relationship between the resistance in a circuit, the current in a circuit, and the voltage, and this is known as Ohm's law. All right. So Ohm discovered a relationship between the resistance, the current, and the voltage in a particular simple DC circuit, and I'll explain what DC means here in just a minute. But he discovered that for any given voltage source, we'll call it V, the relationship between the current and the resistance and the voltage is V equals IR, right? Where I is the current and R is the resistance. All right. Now, technically, current, if we're going to look at it in our pipe flow model, all right, let's look at our pipe again. And let's say we have all sorts of charge here. The way we measure current, right, so here's my pump, and here's my outlet. All right, and so the way we measure current is simply the flow of charge, but mathematically what that means, all right, let's define it mathematically. What that means is that we measure the number of electrons, number of charges that flow past a specific point per unit time. All right. So if I had a giant magnifying glass or a microscope or something, and I looked at this point right here, right, and the pump put in a bunch of energy, and so all of these electrons are flowing this direction, and I count the number of electrons that cross this point every second, right? So maybe in 1 second there are a few 100,000 electrons that cross that line, then the current I would be the total charge that crossed that point over my time interval. Or sometimes we just write it as I equals Q over T. All right, so the total number of charge that crosses some point in time is how we describe the current. All right, and I should mention one thing. All right, this is measured in amps. So the unit of current is amps, and the definition of the amp would be 1 amp is when 1 coulomb of charge flows through a circuit or past a specific point in a circuit in 1 second. All right, this is a pretty big current. And you don't necessarily want to discover this for yourself. All right, this will shock you and most likely cause death. All right. If you absorb 1 amp of current, then it will definitely shock you and it will most likely cause death. All right. So 1 amp is a very large amount of current by most standards. All right. Okay. And so resistance is measured in ohms. Or symbolically, sometimes we use the Greek letter omega. All right. So what this is saying is that Ohm's law says V equals IR. So units wise, that means that the volt is equal to amps times ohms. All right. So this is the equation. These are the units. All right. So the volt is equal to amps times ohms. And the amp would then be volts over ohms, and ohms would be volts over amps. All right. So if we want to get a picture of what this looks like, all right. So let's continue with our pipe flow model, but now let's actually draw a battery, and this will be our pump. And I connect some pipe to that battery, and I complete an entire circuit. All right. So here's my positive terminal, here's my negative terminal. Now we define current to be the direction of the flow of positive charge. So we would say that the direction of the current would flow from the positive terminal, because the positive charges would be repelled away from the terminal, positive terminal. So the flow of charge, the flow of the current is defined to be this direction, when in fact the actual electrons would be going in the opposite direction because they're repelled by the negative end of the battery and attracted to the positive. So the actual flow of current is going this way, but when we talk about the direction of current, we define it to be the direction that a positive charge would move if it were moving. All right? This is a byproduct of Ben Franklin arbitrarily calling positive and negative charges, and he assumed that positive charges could move just like negative charges, and now we know that's not the case. All right, so that's where that came from. So if we look at this, all right, in some detail, we can get a sense of what's going on. So here's my pipe, and notice, all right, I now have my first rule for circuits. All right, so my charges, my current's flowing in this direction, and then it gets recycled. All right, and if you have water with pipe in it, or I'm sorry, if you have a pipe with water in it, then this is exactly what happens, right? If you have a pump and you just have water, it will just continue to cycle this around. Now, where current is a little bit different than water flow is, let's look at Ohm's law. All right, so let's look at Ohm's law. If I rewrite it for I, then I get I equals V over R. All right, I equals V over R. Now here we have no resistance effectively. All right, there's a little bit of resistance in the battery itself. There's some internal resistance here, but effectively there's not really any resistance at all. And also technically the wire has a little bit of resistance in it, but again, it's very, very tiny. For our intents and purposes, it's negligible. So if I have a battery and say this is 1.5 volts divided by no resistance, then this is essentially an infinite amount of current. All right. This is why if you just hook a wire to both ends of a battery, it gets hot very quickly. Right? It gets hot very quickly because there's no resistance to limit the amount of current flowing. All right? Okay, so what does a resistor actually look like? Okay, well, if we look at our pipe flow model, here's my pipe. A resistor would look something like a dam. All right, so here I've dammed up the ability for current to flow, and it can't pass here, and it lets just a little bit of current through, just a little bit. So let's make this a little more dramatic, right? So here we have a lot of current coming out of here, or we have a lot of ability for the current to come out of here, but the dam only lets a little bit through. And this is positive and negative. And then as the current flows through and things get recycled, then only the charges that are moving account for the current. So all of these charges that are dammed up don't account for any more of the current, and only the amount of charge that came into the battery can exit the battery, and you have a nice regulated current. All right, so you have a very nice regulated current. So a resistor just regulates the flow of current. All right, so that is what the resistor does. And when we draw circuit diagrams, all right, we have some symbols, and a battery is denoted as something like this. A wire is just a line, and a resistor is kind of a zigzaggy thing. All right, so your battery is a couple of lines that are large and then some smaller lines, and your wire is just a straight line, and your resistor is a zigzaggy guy. All right, so how does this all get put together? All right, so let's just do a quick example, and let's use Ohm's law. To determine the current in the following situation. All right, so let's say I have a 12-volt battery, maybe something like a car battery, and I have a resistor of, let's say we have a resistor of 24 ohms. And I want to know the current. All right, now, first things first, how is the circuit set up? Well, we have some rules for circuits, right? And the first rule is, for current to flow, the circuit must be a complete loop, all right? So for current to flow, the circuit must form a complete loop. All right, and so what that means is if I just have my battery here, my 12 volts, and some wire here, and then I have my resistor hooked in there, and my wire just, the rest of my wire comes down here and it doesn't connect with my battery, this will produce no current. All right, no current in this circuit. And remember, this is 24 ohms. All right, so this won't produce any current whatsoever. I must connect my wire to the other end of the battery for any current to flow. And now this will produce current. All right, so now I have current. But how much? Right? So remember that V equals IR. That's Ohm's law. And R, sorry, I'm looking for I. We want to solve for I. And doing so, I divide both sides by R. And my R's cancel. And I equals V over R. So I is going to equal 12 volts over 24 ohms. And that gives me 0.5 amps roaming through this circuit. All right? And so you'll notice that just putting in even a few ohms can drive the effective current down quite a bit compared to the case where there's no resistance. And again, this is because if I don't have much resistance at all, then my current is near infinity, although it's not absolutely infinity. It can be well more than a battery or a wire can contain, and that's why sometimes if you hook up things wrong, your batteries can smoke, your wires will start melting, or at least the casing on the wires will start melting. You can potentially start a fire and such things. So you want to make sure you have your resistors hooked in there properly to regulate the flow of current. Alright, so next time we will look at how to hook up series and parallel circuits and do a couple of examples with those, and we will see you next time.